You know that feeling? You're on your phone, maybe wrestling with an app, trying to book something, manage files, whatever,
Mm.
and you click a button, you expect one thing, and bam, something totally different happens.
Yeah, happens all the time.
Or maybe worse, you've got some automated assistant trying to help, and it just gets stuck, clicking the same wrong spot over and over, like a digital broken record.
Oh, absolutely. It's maddening.
It's so frustrating because, for us, it seems obvious what went wrong and what to do next. But
Right.
for AI agents trying to navigate the visual world of our screens or our GUIs, graphical user interfaces, that simple mistake, it can be a total dead end.
And that frustration, it really points to a fundamental challenge, doesn't it? In
Mhm.
building AI agents that are actually, capable for our digital lives.
Oh, so.
Well, current models, they can execute tasks pretty accurately, sometimes impressively so, if the path is clear, if everything's predictable. But the second something unexpected crops up, maybe a button moves after an update, or there's a network glitch, or even if the agent itself just messes up, makes a misstep,
Yeah.
they often lack this ability that we take it for granted, the ability to realize, hang on, that wasn't right, to figure out the problem and then decide how to recover.
Exactly. Like, what if an agent clicks a button and the menu it was looking for just doesn't pop up?
Right.
A person immediately knows, okay, that button didn't work or did something else. I need to try a different button, maybe go back.
Yeah, standard human error correction.
But most current agents just stop. Or they get stuck in a loop. They don't have that oops moment, that capacity for reflection and correction.
And it's precisely that capability, recognizing an error based on what happened, understanding maybe why it happened, and then forming a plan to fix it,
Yeah.
that researchers are now calling reflection. Specifically in this context, AI interacting with GUIs.
Reflection. Okay.
It's not just about ticking off steps in a sequence. It's about handling the messiness of the real digital world.
So what if these agents could learn from those blunders? What if they could look at the screen after they did something and think, that didn't change like I thought it would? Or, whoops, click the wrong thing.
And then intelligently decide, okay, I need to backtrack, or let me try this other approach instead.
That sounds like a huge leap forward, and that's the fascinating problem space we're diving into today, isn't it?
It is. We're digging into a specific research paper. It's titled GUI-Reflection, Empowering Multimodal GUI Models with Self-Reflection Behavior.
GUI-Reflection. Okay, I like it. By Wu and colleagues. And it proposes a powerful new way to build these GUI agents, right?
That's right. This paper tackles that limitation head-on. It proposes a novel framework, a new way of training, designed to explicitly embed self-reflection and error correction skills.
Not just as an add-on at the end.
No, not as an afterthought. Throughout the agent's training process, the goal is to create agents that don't just blindly follow instructions, but can actually recognize, understand, and crucially, bounce back from their own errors.
Okay, let's unpack this paper then. Our mission for this deep dive is to really understand how this GUI reflection framework actually works.
Yeah, there's a lot there.
They've got this multi-stage approach you mentioned, and they break down reflection into specific skills. We need to look at how they train these skills. And I heard something about them automatically generating simulated mistakes. That sounds cool.
Yes, that's a key part of making it scalable.
Okay, so we'll look at that, what their results show, and what this could all mean for the future of those automated tasks we, rely on or maybe wish we could rely on our phones and computers.
It really feels like a significant step towards making these GUI agents not just functional when everything's perfect, but truly robust and adaptable, ready for the complexity of real-world user interfaces.
All right, let's dive in. First things first, let's set the stage a bit more. Why is tackling this GUI automation problem so important in the first place? And where do the AI agents we have today really fall short when, the going gets tough?
Well, GUI automation is pretty fundamental, really, if we want to leverage the full power of our digital devices, both for us as individuals and, across industries.
Right.
It's absolutely critical for boosting productivity. Just imagine automating those repetitive tasks that take minutes, maybe even hours, manually.
Oh, yeah, definitely.
But it's also incredibly important for accessibility, making technology usable for people who might have difficulty with manual interaction.
That's a really good point.
Think about automating complex workflows in business software. managing cloud storage, or even just navigating those really tricky online forms. The potential benefits are just immense.
Totally. And the paper, it kind of outlines the landscape, right, of how people have been trying to build these agents so far. You said there are broadly two main types.
That's right. The first approach they discuss is what they call agent-based frameworks.
Okay, agent-based. Is this like taking a really smart AI, like a big language model, and then giving it a bunch of tools to use?
That's a pretty good analogy, yeah. These frameworks typically build upon very powerful, large foundation models. You know, the big names we hear about like GPT-4o or Gemini, Claude, those sorts of things.
The ones that are good at reasoning.
Exactly. They're excellent at reasoning and understanding instructions. The frameworks then augment them, give them external tools or specific modules designed just for interacting with GUIs.
Ah, so the core AI brain does the thinking and the planning, and then it tells these specialized tools, okay, click here or type this into that box.
Precisely. Often they interact with the interface using structured data, things like accessibility trees.
Accessibility trees, that's like a non-visual map of the screen element.
Yeah, a more organized representation. And the performance of these systems really relies heavily on careful prompt engineering.
Crafting just the right instructions for the big AI brain.
Exactly. Guiding its logic and how it uses the tools.
But as the paper points out, this approach, it has its downsides, especially when things get complicated.
It does. I mean, they can be powerful for well-defined tasks, sure, but these multi-component frameworks, they can be quite computationally expensive.
Makes sense, coordinating different parts.
Yeah, orchestrating interactions between different models and tools takes resources. But more critically, especially for robustness, they're prone to what the paper calls cascaded errors.
Cascaded errors. Sounds bad.
It means a single mistake in just one module. Maybe the foundation model misinterprets an instruction, or a tool fails to execute correctly, that one slip-up can easily derail the entire process.
Right.
It leads to subsequent errors, and then recovery becomes really, really difficult.
Got it. So one weak link can just break the whole chain. Okay, so that's agent-based frameworks. What's the other main way researchers are trying to build these GUI agents?
The second category is end-to-end multimodal GUI models.
End-to-end. Okay, the name kind of suggests everything's integrated, like into a single model.
That's the core distinction, yeah. These models aim to integrate everything. Perception, actually seeing the screen, reasoning, understanding the task in the interface, and action grounding, deciding where exactly to click or what to type. All within a single, unified architecture.
Wow, so they process the visual screen information directly, more like how a human sees and interacts.
That's the idea, more akin to how we do it. Instead of an AI brain telling tools what to do based on, say, an accessibility tree.
Yeah.
It's more like a single AI entity looking at the actual screen image, the pixels, and deciding the next action based purely on what it sees and the instruction.
Okay, that sounds potentially more efficient, maybe more scalable.
Exactly. They offer that promise of greater efficiency and scalability compared to juggling multiple components. And they're also seen as a potentially valuable path towards building more general-purpose AI that can handle all sorts of diverse digital tasks.
And here's the big but this paper focuses on, right? These end-to-end models, they have a critical Achilles heel.
They do. And it stems from how they're usually trained. The standard practice for training these end-to-end multimodal GUI models relies almost exclusively on large data sets of, well, successful interactions.
Successful ones, you mean perfect runs?
Pretty much. Researchers collect demonstrations of humans completing tasks perfectly, or they generate error-free sequences programmatically. The model is then trained simply to imitate these perfect sequences, behavior cloning, basically.
Okay, hang on. Training on success. That seems logical, doesn't it? You want the agent to know how to do the task right. Why is that a major limitation?
Because the real world,
Yeah.
it's just not error-free.
Right, things go wrong.
All the time.
Yeah.
So when these models encounter any deviation from their perfect training data, maybe a slightly different UI layout after an update, an unexpected pop-up window, a slow loading screen, or even if they execute an action incorrectly because something was ambiguous,
Yeah.
they simply don't know what to do. They lack the experience of failure. They haven't been trained to recognize the visual cues that signal an error. They haven't learned to understand why their previous action didn't achieve what they intended, or how to plan a recovery step.
So if they've only ever seen the perfect path to the destination, they have absolutely no roadmap for navigating detours or dead ends. They just
No.
get lost.
Precisely. And the paper makes this really insightful point, almost a paradox.
Okay.
They suggest that even if the underlying large multimodal models these GUI agents are built on initially possess some general reasoning or, reflection capabilities.
And some of them do, right?
Some definitely show signs of it. But the standard process of fine-tuning them solely on perfect, error-free GUI interaction data can actually suppress or actively reduce these latent reflection skills.
Wait, really? The training makes them worse at reflection.
That's the argument. It's like teaching someone only how to follow a perfect script so meticulously that they completely lose the ability to improvise when the script suddenly gets thrown out the window.
That's wild. So the very training designed to make them good at GUI tasks accidentally makes them brittle, makes them worse at handling errors.
It seems that way.
The paper has that really striking figure 1 that illustrates this point, doesn't it?
Yes, figure 1 provides a really powerful visual contrast. On the left side, it shows a typical end-to-end agent trying to do some file task.
Okay.
The agent performs an action, gets a new screen observation, and its internal thought process, its action thought, actually shows some awareness that something's wrong. It might think something like, I am wrong, no size info here, press back.
So it knows it messed up.
It seems to, internally. It continues. File setting is wrong, so probably should be info. Click it. It has the diagnosis, recognizing the error, considering pressing back, identifying a plausible alternative.
It has the right idea.
Exactly. But then its actual predicted action might just be another incorrect click.
Yeah.
Or it gets stuck, or it fails to recover effectively. The thought doesn't translate into the right action for recovery because it hasn't been trained to execute that recovery sequence.
It's like it knows conceptually it's wrong, but it doesn't have the, motor skills or the training to actually do the fixing in the GI environment.
That's a great way to put it. Now contrast that with the right side of figure 1. This shows the behavior they want, what GUI-Reflection is aiming for.
Okay.
The agent takes an action, gets the screen observation, thinks, I'm wrong. No size info here, press back. But crucially, its next predicted action is actually press back.
Ah, it does the rollback.
It successfully executes the rollback. Then, with the screen state reverted, it thinks, file setting is wrong, so probably should be info. Click it. And it proceeds to take the correct next action, successfully completing the task.
That's the difference. It's not just having the thought bubble. It's the capability to translate that recognition of error into effective recovery actions on the screen.
Yes. Bridging that gap between recognizing an error and acting correctly to recover from it is the core challenge here.
And have others tried to tackle this reflection idea before?
Yes, some prior research has touched on reflection. But the authors here note that these earlier efforts often rely on really extensive human annotation of errors and the recovery steps.
Which sounds expensive and slow.
Exactly. Not very scalable. Or other approaches might only focus on teaching reflection in the final online training stage. This paper proposes a new framework that introduces reflection training much earlier and, critically, uses automated methods to generate the necessary training data at scale.
Okay, so the problem is crystal clear. Current end-to-end agents train only on perfection. They just lack the fundamental ability to recognize and recover from errors. They might even lose some latent reflection skills they started with.
Right.
So now, how does GUI-Reflection propose to solve this? What's their big idea?
The big idea behind GUI-Reflection is fundamentally to move away from training only on success. It's simple in concept, but complex in execution.
Okay.
They propose a framework that explicitly teaches and reinforces these self-reflection and error correction capabilities throughout the agent's entire training lifecycle, across multiple distinct stages.
Multiple stages.
So this isn't just a single tweak or fix. It's really a complete shift in the training methodology. You can see the overall structure outlined in figure 2 of the paper.
Multi-stage training. That implies it's like a structured progression, building skills layer by layer.
Absolutely. The framework involves 3 main phases. First, GI-specific pre-training. Second, offline supervised fine-tuning, or SFT. And third, online reflection tuning.
Pre-training, offline SFT, online tuning. Got it.
And the key is that these reflection capabilities are woven into and built upon in each of these stages.
Yeah.
It creates this robust, layered learning process.
So it's not just one type of training, but a sequence that builds different aspects of reflection. It sounds kind of like maybe first learning the basic rules of error handling, like the grammar, then practicing with realistic, maybe simulated mistakes, like writing practice sentences.
Good analogy.
And then finally getting real-world experience where actual errors happen and you learn to fix them on the fly, like having a real conversation.
That analogy really captures the essence of it quite well. And it Importantly, the paper doesn't just treat reflection and error correction as one big, fuzzy skill. They can't just tell the model, be reflective.
Right, that wouldn't work.
No. So they carefully break it down into 3 more specific, fundamental capabilities that an agent needs to master to achieve robust error handling.
Okay, let's nail those 3 capabilities. What are they?
First, there's action verification.
Action verification. Okay.
This is the ability for the agent to look at the screen after it's taken an action and determine whether that action actually achieved its intended purpose, based purely on the resulting screen state.
So, did clicking that button actually open the settings menu I wanted? Or did something else happen?
Exactly. Checking if the outcome matches the expectation. That's the first piece.
Okay, what's second?
Second is action reversal.
Reversal. Makes sense.
If the agent realizes, through verification perhaps, that its last action was wrong or didn't work, it needs to know how to undo it, how to backtrack to a state where it can make a correct attempt.
So that sounds like knowing when and how to hit the back button on your phone, maybe, or finding an undo function within the app itself.
Precisely. Getting back to a known good state, or at least the previous state, is often the critical first step in any recovery process.
Okay, verification reversal. What's the third one?
The third capability is mistake-informed reattempt.
Mistake-informed reattempt. Okay, that sounds a bit more complex.
It is perhaps the most sophisticated of the 3. It's the ability to take the knowledge gained from a failed attempt understanding what went wrong and use that specific information to make a different and hopefully better attempt to achieve the original goal.
So not just hitting back and then immediately trying the exact same wrong thing again, which happens sometimes.
Right, which is classic non-reflective behavior. This is about actually learning from the failure and modifying the next step based on that learning.
Using the error itself as a piece of information to guide the next action. Clever.
That's the crucial part. And by focusing on these 3 specific abilities, verification, reversal, and reattempt, the researchers can then design very targeted training tasks and generate specific data for each one. It makes the overall goal of building a truly reflective agent much more tractable, more achievable.
And they start building these skills right from the very first stage, you said, the GUI pre-training.
Yes, and that's key to their approach. Remember how we discussed that standard GUI pre-training, while great for basic UI understanding and grounding elements, can actually hurt reflection skills?
Yeah, that paradoxical effect.
So stage 1 of GUI-Reflection explicitly adds training aimed at cultivating these foundational action verification, action reversal, and mistake-informed reattempt skills right from the outset, during pre-training.
So they're actively preventing that regression, that loss of skill, and establishing a strong base for reflection early on.
Exactly.
How do they do that? They use something called the GUI-Reflection task suite for this pre-training phase, right? What exactly is that suite?
The GUI-Reflection task suite is essentially a collection of specially designed training tasks. It's the specific method they use during pre-training to teach the model the basic building blocks of recognizing and reacting to errors, but in a very structured, focused way.
A targeted intervention, basically.
Precisely. It's designed to embed these reflection capabilities early.
So it contains specific training data tailored for those 3 capabilities we just talked about: verification, reversal, reattempt.
Exactly. Let's walk through how they structure each task, maybe using the examples they show in Figure 3. It makes it clear.
Okay, sounds good. First up is action verification.
Right. This is where the agent checks if an action achieved its purpose.
Okay.
For the training data for this task, the model is presented with 2 screenshots, one taken before an action happened and one taken after the action occurred.
Before and after. Got it.
It's also given a description of a potential purpose or goal for that action. And the task for the model is simply to output yes or no.
Yes or no. Did the action successfully achieve that stated purpose? Did it cause the right change between the before and after screenshots?
Exactly.
Yeah.
Like in Figure 3, the left panel, they show screenshots before and after some action, and they asked, did this action achieve the purpose? Search for Northern Lights, Iceland itinerary, or maybe follow the northern.lights.icelandics user account.
And the model just has to look at the visual change, or maybe the lack of change, and decide if the purpose was fulfilled.
Right. Now, how do they create this data? This is one of the really clever parts. They use automated methods. They don't have humans labeling all this.
Automation again? How does that work here?
They sample screenshot pairs and the actions connecting them from existing large data sets of GUI interactions. Then they deploy another powerful language model, basically acting as an automated annotator.
Okay.
For an action that was actually successfully executed in the original data, this annotator model can identify the true purpose that was achieved. That becomes a positive training example. Action X, achieve purpose Y, yes.
Makes sense.
But it also generates a plausible false purpose. Something that sounds reasonable for that screen or action, but wasn't actually accomplished by that specific action. That becomes a negative training example. Action X achieved purpose Z, no.
Ah, so it learns to distinguish true outcomes from plausible sounding but incorrect ones.
Exactly. And this automated process can generate the huge number of yes-no question-answer pairs needed to effectively train this verification skill. They mentioned the prompts used for this in the appendix, showing how they guide the annotator model.
That's really smart. They don't need an army of humans clicking yes or no. They just use AI to create the labels automatically. Okay, what about the second task in the suite, action reversal?
Action reversal, shown in the middle panel of Figure 3, trains the agent's ability to backtrack. When it makes a mistake, it needs to know, okay, how do I undo that last incorrect action to get back to where I was so I can try again?
Right, the undo skill.
The training sample for this shows screenshots before and after a particular action. Let's say the action was click the messages icon. Then it asks the model to identify the correct action required to revert the screen state back to the before screenshot.
And Figure 3 shows this as a multiple choice question, is that right?
Yes, the example there shows those screenshots around clicking the messages icon, and the question is something like, choose the undo action. It then provides several potential options, A through F, like clicking various other icons, home icon, search icon, etc.
And the model has to pick the one that would take it back.
Exactly. The correct answer is the action that would most likely return the user to the state they were in prior to clicking the messages icon. In that specific example, it's clicking the home icon. They even sometimes highlight the original click location with a visual marker, like a red circle, in the training data to provide context.
And how is this data generated automatically, also using language models?
Similar process, yeah. They use automated methods on existing data sets. They sample actions and the corresponding before and after screenshot pairs. A language model is then used to identify the most appropriate undo action for that specific sampled action. It prioritizes in-app revert options if they're obvious, like a cancel button, or maybe defaults to a general pressback action if no specific revert is apparent.
Okay.
Then another language model, maybe a faster, smaller one, is used to generate a set of plausible but incorrect options for the multiple choice question, just to make the task challenging. This automated process creates the diverse training data needed for teaching action reversal.
Okay, so simulating the need to undo and how to do it. What's the third task in the pre-training suite? Mistake-informed reattempt.
Yes, mistake-informed reattempt. This is shown on the right in Figure 3. This task specifically targets the agent's ability to learn from a grounding error.
A grounding error. You mean like it tries to identify and interact with a specific button or element on the screen, but it incorrectly selects the wrong one. It grounds the instruction to the wrong place.
Exactly that. Maybe the instruction was click login, but the agent mistakenly targeted the bounding box for the sign-up button right next to it.
Okay.
The goal here is to teach the model to use the information about its own failed grounding attempt to make a more accurate attempt the next time.
How does the training data look for this?
The training sample provides the initial task instruction like favorite the music. It shows the screenshot. And critically, it shows the model's first attempt, which is an incorrect prediction of the bounding box or element to interact with. This incorrect attempt is often visually highlighted on the screenshot, maybe with a red bounding box.
So the model sees its own mistake?
Yes. Then, it presents the same screenshot again, but with a slightly modified instruction for the second attempt. This new instruction explicitly points out that the previous attempt was wrong. It might say something like, you predicted wrong element box, which is incorrect. Now find the correct element for favorite the music.
Ah, okay. So it's like saying, you tried to click here, pointing to the wrong spot. That was wrong. Now find and click the right spot for the original task.
Exactly. The model's task is then to predict the correct bounding box or element for the original instruction, favorite the music, on that same screen. But now, crucially, having been explicitly told about its previous mistake.
Does it only learn from one mistake?
Actually, the data generation pipeline is quite sophisticated here. They can even create training samples where the agent made multiple incorrect grounding predictions in a row on the same screen. The input might show up to 5 previous incorrect attempts, all highlighted with red bounding boxes, before asking the model for the final correct prediction.
Wow. How do they find these errors to create the data?
They analyze existing GUI interaction datasets using a pre-trained model to identify common points where grounding errors tend to occur. Once they have these examples of failures, automated prompts are used to construct these training samples. The instruction, the screen, the simulated incorrect predictions marked in red, and the expected correct target output.
Okay, so stage one, the pre-training stage, is all about building these fundamental, somewhat isolated reflection skills, checking outcomes with action verification, knowing how to undo with action reversal, and using mistake information for better grounding with mistake-informed reattempt.
Correct.
And all of this is done using this GUI-Reflection task suite, which is populated with automatically generated training data right in the initial pre-training phase.
Exactly. It's like giving the model the basic vocabulary and grammar of error handling before it has to start stringing together complex sentences of recovery in real situations. It lays the foundation.
All right, that makes sense. We've got the foundational skills built during pre-training. Now we move on to stage two. This is where the paper talks about learning reflection from simulated but more complex mistakes during the offline supervised fine-tuning SFT phase.
Right.
We already established that standard SFT, just training on perfect successful data, is a problem because it doesn't teach error handling.
Precisely. Because standard SFT trains the model solely on imitating these perfect trajectories, the model just never sees what happens when things go wrong in a sequence. Or, more importantly, how to recover from those multi-step errors. This severely limits its ability to handle the kinds of errors it's inevitably going to encounter in the real world.
So the goal of stage two is to fix that, to expose the model to a much wider variety of error and recovery scenarios during this offline training phase.
Yes, but critically, without requiring the enormous amount of manual human effort that would normally be needed to create such error and recovery data.
Okay, so the big challenge here is, how do you create realistic feeling error sequences and the corresponding reflection and recovery steps automatically, especially starting just from existing successful paths?
Exactly. And this is where the really innovative, scalable automatic data pipeline for reflection-oriented SFT data comes into play. They detail this in section 2.4. They developed methods to take successful task trajectories and programmatically introduce errors, and then automatically annotate the correct reflection and recovery steps that should follow that introduced error.
Automatically turning success into failure and then figuring out the fix. That sounds incredibly difficult. How does that work?
They use 2 primary automated methods to achieve this. The first one they describe is called goal modification.
Goal modification. So, changing the task's goal somehow, how does that simulate an error?
The core idea, which they explain more in Appendix G, is actually quite clever. They start with this successful, completely error-free tasks demonstration, a sequence of steps. They pick a specific step somewhere within that successful trajectory. Let's say step T. Then they use a powerful language model, like Gemini Pro they mention, to slightly modify the overall goal of the entire task.
Just tweak the goal a little bit.
Yeah, just enough. The modified goal is crafted very carefully using specific prompts, like the example in Table 12. It's designed so that the action that was originally correct at that chosen step T in the original trajectory now becomes incorrect, or at least suboptimal, given the new slightly different goal.
Ah, I see.
The prompt also ensures the modified goal is plausible, maybe something a user might actually ask for, and that the original action now looks like a reasonable mistake someone unfamiliar with the app or the new task might make. And importantly, the steps before step 2 in the original trajectory still need to make sense in the context of the new modified goal, so the path up to the mistake feels consistent.
Okay, so you've used an LLM to change the goal, which makes the original action at step 2 suddenly look like a mistake. Now you have a simulated error. How does that generate the actual reflection training data?
Right, now that they have this simulated incorrect action at step 2 and the screen state that results from it, they use language models again. This time to automatically annotate the sequence of actions and thoughts that should follow in order to recover from this mistake and successfully achieve the modified goal.
Okay, so annotating the recovery path.
Yes. So at the step immediately after the simulated incorrect action, let's call it step 2+1, the agent's internal thought process, its action thought, is annotated to include recognition of the mistake made at step T. The predicted action for step T+1 might then be a rollback action, like press back, especially if the mistake led to a screen state from which direct recovery towards the new goal is difficult.
And if it simulates pressing back, does the annotation stop there?
No, if the simulated action at step 10 plus 1 is indeed press back, they then generate the training data for the next step as well, step 10 plus 2. Assuming press back successfully returns the screen state to what it was before the mistake at step T, the training data generated for step T plus 2 includes an action thought, where the agent explicitly summarizes the previous error. Okay, I clicked the wrong thing trying to achieve the new goal, reflects on maybe why it failed, and then predicts the correct action sequence needed to pursue the modified goal, starting from that restored state.
Wow.
This whole automated process effectively creates these multi-step training sequences. They show an agent making a mistake due to the goal change, potentially backtracking, and then correcting its approach based on reflection, all geared towards the new goal.
So they're automatically creating quite complex error sequences, not just isolated single errors, and the reflective thought process that goes with recovery.
That's impressive.
Figure 7 in the paper gives an example of this goal modification approach, right?
It does. Figure 7 shows a sequence. It starts with an initial screen, then it shows the screen after a simulated incorrect click has happened, marked with a red dot. This click is incorrect because the underlying task goal was modified behind the scenes.
Okay.
It then shows a screen state after the agent has taken a rollback action, maybe a pressed cancel or back in the previous step, though that exact rollback step isn't explicitly shown as step 10 plus 1 in that figure. But crucially, it shows the agent's action thought at step 10 plus 2 after the rollback.
And what does the thought say?
It clearly articulates the mistake and the recovery plan. Something like, in the previous step, I mistakenly clicked the alarm time. To correct this, I need to close the settings dialog first. I will click the cancel button. It demonstrates the agent's thought process after recovering from the error state, reflecting on the mistake, and planning the corrected path forward based on the modified goal.
That's incredibly insightful, automatically generating the agent's internal monologue about the mistake it made and how it's fixing it. Okay, that's goal modification. What was the second automated approach they used for creating this reflection SFT data?
The second automated approach is called inserting ineffective actions.
Inserting ineffective actions. Okay. How does this one work? Does it also change the goal?
No, this method keeps the original task goal completely unchanged. What they do here is take a step from a successful trajectory, step T, along with its correct action at.
Okay, a normal successful step.
Then they insert an additional simulated incorrect action just before the original correct action at. The key here is that this newly inserted action is deliberately chosen to be ineffective.
Ineffective, meaning
Yeah.
it doesn't actually do anything.
Exactly. It's an action that doesn't actually change the screen state. Think about trying to click on a piece of static text that isn't interactive, or maybe scrolling down when you're already at the very bottom of the page.
Okay, actions that have no visual effect.
Right. They use a language model again, maybe a smaller, faster one like Gemini Flash they mention, to identify plausible ineffective actions for a given screen state and the context of the task. The prompt is in Table 16.
So they insert this useless action. Then what?
Once they have this simulated ineffective action inserted just before the original correct action, they then modify the action thought that corresponds to the original correct action at that follows it.
Modify the thought to acknowledge the useless action that just happened.
Yes, precisely. The agent's internal thought for the correct step at is altered to include reflection on the ineffective action that supposedly just occurred right before it.
Even though the screen looks exactly the same.
Exactly. Even though the screen visually hasn't changed from before the ineffective action, the training data includes the agent's recognition that the previous action was ineffective. The thought might be something like, I see that clicking all files in the previous step did not change the screen, indicating it was an incorrect action. And then it pivots back to the correct approach, to proceed with the task. The correct way is to click the Select File to Open button. They also make sure to edit out any parts of the original thought for action at that might have incorrectly suggested progress was made by the ineffective action.
So this method is essentially teaching this agent to recognize when its own action had absolutely no effect on the screen state, understand that this probably means it was a mistake or a useless action, and then still proceed with the correct next step for the original task.
Exactly. It teaches resilience to non-progressing actions. Figure 8 in the paper visually demonstrates this approach.
How does that look?
It shows a screen. Then it indicates a simulated ineffective click, again a red dot, on something like all files, which importantly didn't change the screen. Then it shows the action thought for the next step, which is the original correct step from the successful trajectory. And that thought clearly reflects on the uselessness of the previous click before identifying the actual button needed for the task.
These are both really clever ways to simulate quite diverse types of errors, either getting off track due to a goal misunderstanding or taking pointless actions and generating the corresponding reflective thought processes, all without needing any humans to manually label errors.
They really are, and this automated generation is absolutely critical for making this approach scalable. The paper mentions using these methods on a large dataset called Android Control to generate over 30,000 new training samples, specifically for reflection-oriented offline SFT.
30,000! That's way more than you could reasonably get with human annotation.
Absolutely. So Stage 2 effectively floods the model with diverse examples of what errors look like in sequence and how to think about them and plan recovery, giving it a much more robust understanding before it has to face the chaos of the real world.
Okay, that makes perfect sense. So we've built foundational skills in pre-training, stage 1. We've learned from lots of automatically synthesized complex errors in offline SFT, stage 2. But as you said, the real world is the ultimate test. That brings us to stage 3, iterative online reflection tuning. This is where the agent learns from actual, real mistakes it makes while interacting live.
Precisely. While that offline training is essential for building broad capabilities and exposing the model to many different types of errors in a controlled way, nothing truly replaces interacting with a dynamic, unpredictable environment. This online stage, covered in Section 2.5, is where the agent gets that real-world experience. It makes genuine mistakes based on the live interaction, and it learns to adapt on the fly.
So for this, they needed a specific environment, right? Not just static data sets.
Yes, they developed quite a sophisticated online environment, detailed in Appendix H. It's specifically designed for training and evaluating these mobile GUI agents.
What's it like?
It's built on Android, using Android emulators. And it's designed to be highly diverse, efficient, and scalable to support this iterative training process, which requires a lot of interaction.
Diverse in what way? What kind of tasks does this environment present to the agent?
It includes 215 distinct task templates. These span 11 different real-world Android apps. They list examples in Table 21, things like the Clock app, Contacts, Chrome browser, Calendar, Files, Settings, common apps.
Okay, real apps. And templates mean they're not always the exact same task?
Right. These templates are highly configurable. They can be instantiated with different parameters each time, different contact names, different alarm times, different websites to visit, etc. This creates a vast number of specific task instances from those 215 templates.
So the agent can't just memorize fixed sequences, it has to learn to generalize.
Exactly. And they also structure the tasks by difficulty.
Ah, you mentioned difficulty levels.
Yes. The tasks are categorized into Level 1, which includes 135 somewhat easier tasks, and Level 2, which has 80 more complex multi-step tasks that often require navigating across different screens or handling more nuanced interactions.
And that allows for curriculum learning, I guess. Starting easier and getting harder.
Precisely. We'll come back to that. The environment itself is also built as a distributed system. A host coordinates multiple worker machines running emulators, allowing them to run many training interaction instances in parallel, making the whole process much more efficient.
Okay, efficient and diverse tasks. How does the system actually know if the agent is performing correctly during this live online interaction? Is it watching the screen?
They use robust verification methods, also detailed in Appendix H. For many tasks, they can use programmatic verifiers. These directly check the actual system state or maybe a database entry on the emulator to definitively confirm if the task goal was achieved. For example, did the contact actually get saved? Was the alarm set correctly?
That sounds pretty reliable.
It is, when possible. But for tasks where checking the system state isn't enough or isn't feasible, they use powerful language models as MLLM-based verifiers.
Using AI to check the AI.
Kind of, yeah. These verifier models are given the original task instruction, the history of actions the agent took, and the sequence of screenshots. Based on all that context, they determine if the overall task was successful.
Oh, okay.
But crucially, this MLLM verifier can also be prompted, using a prompt like in Table 19, to assess the correctness of each individual step the agent took along the way.
Ah, so the system can tell if the agent took a wrong turn, made an inefficient move, even if it somehow stumbled its way to the final correct state eventually.
Exactly. This stepwise verification is absolutely key for generating high-quality, fine-grained training data from these online interactions. It's not just pass-fail for the whole task.
Okay, so they have this environment and these verifiers. Now, how do they actually train the model using this online setup? You mentioned an iterative online reflection tuning algorithm, Figure 4, Section 2.5.2.
Yes, iterative is the key word. It's a cycle.
A loop.
Exactly. In each iteration of the cycle, the current version of the agent interacts with the online environment, attempting to complete various tasks drawn from the task pool. This interaction generates a set of trajectories, or rollouts. Some will be successful, many, especially early on, will be unsuccessful. The system collects all this interaction data, the actions, the thoughts, the screenshots.
And then it uses all this new data to improve the model for the next round.
Yes, but first, the collected data is very carefully processed and filtered. This is important. For the trajectories that were marked as successful overall by the verifier.
Yeah.
They don't just keep the entire sequence as is. They use that stepwise MLLM verifier we just talked about to check if every single action taken within that successful trajectory was actually correct and reasonably efficient. Only the steps deemed correct are kept for training.
So they filter out any meandering or inefficient detours, even if the agent eventually got the right answer. They only learn from the good parts of successful runs.
Right. Now, what about the unsuccessful trajectories? These are perhaps even more valuable for learning reflection.
How do they handle those?
They also extract the good parts first. Using another language model, specifically prompted for error localization, like in Table 20, they pinpoint the first step within the failed trajectory where the agent took an incorrect action.
Finding the point where things went wrong.
Exactly. All the correct steps the agent took before that first error occurred are valuable data, showing correct initial behavior. So those are kept for training as well.
Okay, so even in failures, they extract valuable examples of correct initial steps. But where does the crucial reflection training data come from in these real online failures?
This is where the automated annotation process, similar to what they used in the offline SFT stage, gets adapted and applied to these genuine online errors. For that identified first incorrect action in a failed trajectory,
Yeah.
the system automatically annotates two key things. First, it annotates what the correct action should have been at that step. This serves as a pre-error correction training target.
Like, you clicked X, which was wrong. You should have clicked Y, which was correct.
Exactly that kind of signal. Second, it annotates a post-error reflection action. This represents the action the agent takes immediately after making the mistake. But crucially, it includes the necessary reflective thought process within the action thought. I made a mistake by clicking X, now I need to do Z to recover.
So if the agent actually misclicked in the online environment, the system automatically generates the training data pair. First, telling it the correct click it missed, and second, for the very next step the agent actually took after that misclick, the system annotates what the agent's thought and action should have been to start the recovery process.
Precisely. And if the agent's actual response right after the error was just to press back, the system goes even further. It annotates the step after pressing back as well.
What does that annotation look like?
For this step, the one after pressing back, the training data includes the agent's thought, summarizing the mistake it just recovered from, reflecting on it, and then attempting the correct path towards the goal, starting from the restored screen state. Powerful language models like Gemini Flash and GPT-4o they mentioned are used for all these automated annotations in the online setting, guided by the task information and interaction history from the environment.
That's incredible. They're automatically generating targeted reflection training data directly from the agent's own actual failures in the live environment.
It creates this powerful closed loop of learning. The agent fails, the system analyzes the failure, generates corrective training data based on that specific failure, and uses that data to improve the agent.
So the full data set used for fine-tuning in each iteration is a mix.
Yes, it's a combination of the correctly executed steps filtered from successful trajectories, the correct initial steps extracted from failed trajectories before the first error, and these automatically annotated error reflection recovery sequences generated directly from the failures themselves. This combined data set is then used to fine-tune the model, hopefully making it better prepared for the next iteration of interaction.
Okay, that's the data collection and annotation. How do they decide which tasks the agent even attempts in each iteration? Does it just try random tasks from the pool?
No, they use a smarter approach called dynamic weighted sampling.
Dynamic weighted sampling.
The system keeps track of the model's success rates on different tasks or maybe different apps within the environment. In the next iteration of interaction, Tasks where the model had lower success rates in the previous iteration are sampled more frequently.
Ah, so it automatically focuses the agent's practice on the things it finds most difficult.
Exactly. It directs the learning effort where it's most needed. Like a good coach giving you extra drills on your weak points.
That's smart. And this links back to the curriculum learning you mentioned earlier, with the difficulty levels.
Yes, exactly. Section 2.5.2. They typically start the online tuning process primarily with the easier level 1 tasks. Once the model achieves a certain performance threshold on those, or maybe after a set number of iterations, they start introducing the harder level 2 tasks, or perhaps a mix of the most challenging level 1 tasks and the new level 2 tasks. This structured curriculum ensures the agent builds skills incrementally, tackling more complexity gradually as it improves.
Okay, so stage 3 is really the crucible, isn't it? It's real-world interaction, generating targeted training data directly from actual mistakes, using sophisticated automated annotation, and then continuously improving the agent through this iterative tuning cycle, using dynamic sampling to focus on weaknesses, and following a curriculum from easier to harder tasks.
That's a great summary. It's where all the pieces, the foundational skills from pre-training, the error pattern recognition from offline SFT really come together, and the agent learns to handle the unpredictable nuances of real GUIs by actually experiencing and recovering from failure in a structured way.
Yeah. Okay, we've walked through the problem why current agents fail and the 3 detailed stages of the GUI-Reflection framework designed to fix it. Now, for the crucial part, the proof. Did all this complex multi-stage reflection training actually work? Did it make the agent significantly better at handling errors and performing tasks? What did the experiment show?
Yeah, the payoff question. And the experimental results presented in the paper are actually quite convincing. They directly address the core claims they make. Let's first look at how well the models performed on those foundational reflection skills, the ones evaluated by their own GUI-Reflection task suite. That's Table 1A and 1B in Section 3.2.
Okay, they tested several different models here, didn't they? Including some powerful large closed source ones like Gemini and GPT-4o, and also open source base models, comparing them to their own models trained with and without their reflection methods.
Exactly. Table 1A shows the performance on action verification,
Yeah.
do the action work, and action reversal, how to undo. Now, many models show some reasonable capability here, especially those large, powerful closed-source ones. But here's where it gets really interesting, and it confirms their initial hypothesis about the dangers of standard training.
Mhm.
Look closely at the comparison between a base open-source model, like InternVial 2.5 8B they use,
Okay.
and that exact same model after it undergoes standard GUI pre-training, the row labeled UI pre-train 8B.
Whoa. Okay, I see it. The standard GUI pre-train 8B model performs worse than its original base model. On both action verification, it drops from 62.76% down to 57.95%. And on action reversal, it drops from 48.33% down to 40.71%.
See, that's the regression effect they predicted. Standard GUI training, because it's focused only on success, actually diminished the base model's existing, albeit imperfect, reflection skills. It made it worse at checking outcomes and knowing how to undo.
That's fascinating. Kind of worrying about standard methods. Now, what about their model trained with the GUI-Reflection task suite data during that pre-training stage, the one labeled GUI pre-train ref 8B?
Look at those numbers. It's a massive leap. Its action verification score jumps all the way up to 87.56%.
Huge jump.
And action reversal goes from that 40% after standard pre-training, or 48% for the base model, all the way up to 93.81%.
Wow, over 93% on knowing how to reverse an action.
That's not just some incremental improvement. It's really a transformation in capability for these specific skills. Training with their targeted reflection suite data during pre-training didn't just prevent the regression, it boosted these fundamental skills dramatically. It made their model highly proficient at recognizing errors and knowing how to undo them, performing on par with or even exceeding much larger, more powerful models on these specific reflection tasks.
Okay, that's very convincing for verification and reversal. What about the third foundational skill, mistake-informed reattempt? Can the model actually use the information about a failed grounding attempt, those red boxes, to do better next time?
Table 1B shows the results for this task. They measure performance across multiple attempts, specifically looking at the success rate on the first try versus the success rate by the third try, pass at 3. What you see is that standard models, including their own basic GI pre-trained model, they show pretty limited improvement from the first attempt to the subsequent attempts. Their pass at 3 rate isn't much higher than their first attempt success rate. This strongly suggests they aren't effectively using the feedback about the previous mistake.
Basically, they're not really learning from seeing those red boxes showing where they went wrong.
Exactly. But now look at the GUI pre-trained ref model, the one trained with their reflection task suite. It shows a much steeper improvement curve from the first attempt to the second and third. Its success rate on the third attempt is significantly higher than its pass rate after just one attempt. This indicates it's much more effectively utilizing the information provided about previous failures to refine its prediction and make better reattempts.
So stage one, the pre-training with the task suite, clearly succeeds at building these core foundational reflection competencies. That's clear.
Yes, the evidence for stage one is strong.
Okay, the foundational skills are demonstrably improved. But does training on those more complex synthesized errors in stage two, offline SFT, and then the real online errors in stage three, online tuning, actually translate to better performance on complex tasks that require putting these skills together for actual error handling and recovery?
That's the critical question, right? Does it help with overall task success? Table 2 presents the crucial ablation study that directly answers this. This is in section 3.3. They evaluate the model's performance specifically on those complex level 2 tasks within their online environment.
The hard ones.
The hard ones. The baseline model, which is trained only with filtered behavior cloning, meaning it only learns from the correct steps extracted from successful paths, no explicit error handling training.
How does it do?
It has a very low success rate on these complex tasks.
Just 14.58%. Wow. Okay, that clearly shows how hard those level 2 tasks are and how insufficient just training on success really is for complex real-world style interactions.
Absolutely. Then they take that baseline and add the reflection-oriented training data generated from their automated pipeline during the offline SFT stage, stage 2. So adding learning from those synthesized goal modification and ineffective action errors.
And what happens to the success rate?
It jumps significantly.
From 14.58% up to 23.61%. Okay, so injecting those simulated errors and recovery sequences during offline training makes a really big difference on actual complex task performance.
A substantial increase, yeah. It shows the value of seeing those error patterns offline. But the biggest leap comes when they add the final stage, the iterative online reflection tuning, stage 3. Learning from real mistakes.
The success rate jumps again.
Jumps again, all the way up to 34.72%.
Okay, that table is really crystal clear evidence, isn't it? It shows that each stage of adding reflection training, the pre-training suite, implicit in the ref model base, the offline SFT with synthesized errors, and the online tuning with real errors builds upon the last and significantly boosts the agent's ability to handle complex tasks in a realistic environment.
Exactly. The offline SFT with synthesized errors helps build robustness, and then the online learning from actual mistakes provides another major performance increase on top of that. It really shows that reflection isn't just some theoretical nice-to-have. Training for it directly and systematically leads to much more capable and resilient agents.
The learning curve they show in Figure 5 visually reinforces this point too, doesn't it? Showing the progress over time during the online stage.
It does, yes. Figure 5 plots the performance across the iterations of online training. You can see the model quickly gets good at the easier level 1 tasks, mastering most of them relatively early.
Right, the blue line goes up fast.
Yeah. But for the more complex level 2 tasks, the orange line, the performance starts lower, naturally, but it shows this consistent, steady upward trend throughout the iterations. It demonstrates continuous learning and improvement as the agent encounters more diverse real failures in the online environment and learns how to handle them through that iterative annotation and fine-tuning loop.
And the curriculum learning aspect, introducing the harder tasks later, keeps pushing that performance boundary upwards, preventing it from just plateauing on the easy stuff.
Exactly. The combination of the automated data generation for offline, the structured multi-stage training, and this iterative online learning loop with dynamic sampling and curriculum learning seem to be very effective at teaching the agent to be resilient.
Okay, so the approach works. How does their final, fully trained model, the GUI-Reflection 8B, stack up in terms of general task performance against other existing models out there? Does all this focus on reflection hurt its ability to just do normal tasks?
That's a fair question. Table 3 shows its performance on a standard general benchmark called Android World. This tests a wide variety of tasks. Their full GUI-Reflection 8B model achieves a success rate of 34.5% on this benchmark.
34.5%. How does that compare?
It's actually quite competitive among other end-to-end models of similar scale in that 8 billion parameter range. What this suggests is that integrating all this reflection training doesn't seem to harm the model's fundamental ability to perform general GUI tasks. It maintains strong general performance while gaining these crucial error handling and reflection skills.
So it gets the best of both worlds.
It seems to strike a good balance. Now, it's true that some much larger proprietary models, or perhaps the best agent-based systems that use external tools, might achieve higher absolute success rates on some benchmarks. But GUI-Reflection demonstrates a really powerful and, importantly, scalable approach for building robust reflection capabilities directly into end-to-end models, which has traditionally been a very challenging paradigm for error handling.
Okay, the experimental results are really convincing. They show that this multi-stage framework genuinely works. It prevents the loss of reflection skills during training, it dramatically improves those foundational error handling abilities, and it significantly boosts performance on complex tasks by enabling the agent to learn effectively from both simulated and real mistakes.
Yes, the evidence strongly supports their claims.
So let's bring this to life a bit. What does this actually look like when the agent is running, when it's exhibiting this reflection? And maybe most importantly, why does all this matter to you, our listener, dealing with your own devices every day?
Okay, yeah, let's bring it back to the real world. The examples they show in Figure 6 of the paper do a great job of visualizing this reflection behavior in action.
What do they show?
Well, the top left example shows the agent identifying and undoing a misclick. It's similar to that alarm setting example we discussed conceptually earlier. The agent clicks something, maybe the wrong time setting. It observes the screen, realizes, whoops, that's not the state I expected or wanted, and then its next action is corrective, maybe pressing a cancel button or the system back button to get out of that unexpected menu.
That's that moment where it basically goes, nope, that wasn't it, let me reset.
Exactly.
Mm-hmm.
Then, the top right example demonstrates the agent recognizing an ineffective action. Remember that training data. Here it is in practice. The agent might click on a piece of text or an icon that isn't actually interactive, something that doesn't trigger any change on the screen.
Right.
The agent's internal action thought shows it recognizing this lack of change. It thinks something like, I see that clicking all files in the previous step did not change the screen, and it understands the implication, indicating it was an incorrect action.
So it doesn't just sit there confused or try clicking it again.
No, it understands the feedback, or lack thereof, and then pivots to identify and perform the correct next action needed for the task. Its thought continues, the correct way. Click the Select File to Open button. It finds the actual button it needed all along.
So it doesn't just randomly try again after a failure. It actually analyzes why the previous action failed in this case, because it had no effect, and uses that specific information to inform its next attempt.
Precisely. It's observing the outcome, reasoning about it, and adjusting its plan. Then, the bottom example in Figure 6 shows recovery from an even more significant error. The agent actually opened the entirely wrong application.
Oh, wow. How does it handle that?
The task was supposed to use an app called Simple Calendar Pro, but the agent mistakenly clicked the standard Google Calendar icon instead. Look at its action thought at Step 2, after realizing it's in the wrong app. I intended to open the Simple Calendar Pro app, but I mistakenly clicked the Google Calendar app icon. Now I am in the Google Calendar app, which is not the correct app for this task.
That's incredibly clear self-awareness of the error.
Yeah.
It knows exactly what it did wrong and where it ended up.
Yes. And then comes the plan for recovery. I need to go back to the app drawer to find and open the correct Simple Calendar Pro app. Step 3 then shows the execution of this plan and continued reflection as it navigates back. Its action thought there is something like, I am currently in the app drawer. I previously clicked the wrong calendar app. I need to find the correct app. I see 2 calendar apps here. The correct one is the orange icon. I will click this icon now.
It even uses visual cues like the app icon color, combined with its memory of the task goal and its previous error, to navigate back and select the correct application this time. That's really impressive recovery from a major initial mistake.
These examples are powerful, aren't they? They really show agents moving beyond just simple command execution. They're exhibiting a form of digital self-awareness, a problem-solving capability when they encounter errors.
Definitely. So wrapping this up, what does this mean for the bigger picture of GUI automation? What's the takeaway?
Well, in conclusion, as the paper states in Section 4, the GUI-Reflection framework really represents a significant advancement in this field. They've successfully managed to integrate these crucial self-reflection and error correction capabilities directly into end-to-end geo models. And they did it through this novel, multi-stage training process.
And critically, using those scalable, automated data generation techniques for the offline stages and that effective online learning loop for adapting to real-world situations.
Exactly. That automation and the structured learning process are key to making this practical.
So let's connect it back. Why should you, our listener, care about this research? What does it actually mean for your day-to-day experience with technology?
Because this framework and the ideas behind it are paving the way for GUI automation that could be vastly more robust, much more adaptable, and fundamentally more reliable than what we typically see today. Imagine having an AI agent that can genuinely help you with complex tasks on your phone or your computer. Things like filling out really detailed online forms, managing various online accounts, or automating workflows that span across multiple different apps.
Tasks that are often tedious or error-prone for humans, too.
Exactly. And imagine that agent being able to handle it even when the UI changes slightly after an update, or an unexpected error message pops up, or even if you yourself make a mistake that initially throws the agent off course.
An agent that doesn't just give up when things aren't perfect.
Precisely. Agents that can recognize they're off track and actually figure out how to get back on course will be far more trustworthy and, frankly, far more useful for everyday productivity. And also for making technology genuinely more accessible for everyone. It really shifts these agents from being somewhat fragile tools that break easily when the environment isn't exactly as expected,
Yeah.
to becoming more resilient, more helpful partners in navigating our increasingly complex digital lives.
It really sounds like moving from a robot that can only follow a perfect, pre-programmed script to one that can actually improvise, adapt, and recover when the unexpected inevitably happens.
That's a great way to summarize the potential shift. Now, it's important to note, the authors themselves are very clear about the current limitations of this specific work. They mention this in Appendix B.
Okay, what are the main limitations?
Well, while they've made really great strides in handling visual errors, action grounding errors, or relatively simple navigation mistakes, their current framework doesn't really cover more complex types of errors. Things like fundamental planning failures, where the agent's overall strategy for a multi-step task was flawed from the beginning.
Ah, so they can recover from clicking the wrong button, but maybe not yet from deciding to approach a complex multi-stage task in completely the wrong order in the first place.
That's a good way to think about it. They're primarily tackling the how of recovery from execution errors, but perhaps less so the what of fixing higher-level strategic errors.
Mm.
Also, their work currently focuses primarily on mobile environments, on Android,
Right.
while the core principles of reflection and the multi-stage training should generalize. Applying this framework effectively to, say, desktop interfaces or complex web browsers would likely require significant adaptation, new data collection, and possibly new techniques tailored to those specific GUI types.
Makes sense. The paper also briefly touches on the broader societal impacts of developing this kind of highly capable automation technology, doesn't it, in Appendix C?
Yes, they do. And it's important to consider. The potential positive impacts are pretty clear. Increased productivity for individuals and businesses, and potentially greatly enhanced digital accessibility for people who currently face challenges interacting with standard interfaces.
Those are big positives.
Definitely. However, as with any powerful automation capability, there are also potential risks that need careful consideration. These sophisticated agents, if not developed responsibly, could potentially be misused. For instance, in things like automated online manipulation or generating spam at scale.
Right, the dual use potential.
Right. Exactly. Also, while their data generation is automated, which is great for scale, relying heavily on synthetic data generated by other AI models requires ongoing vigilance to avoid inadvertently embedding or amplifying biases that might be present in the original source data or within the generative models themselves. The paper rightly emphasizes the need for responsible development and deployment practices, being aware of these risks, and actively working toward building trustworthy AI systems.
It's always a good reminder, isn't it? The more capable we make AI, the more critical it becomes to think deeply about the implications and ensure these powerful tools are used safely and beneficently.
Absolutely. The potential benefits are truly exciting, but they come hand in hand with a significant responsibility to deploy these technologies thoughtfully and ethically.
Okay, well, that was truly a deep dive into the fascinating world of teaching AI agents not just to act, but to learn from their mistakes on our screen interfaces. We saw how these researchers are explicitly building reflection skills, verification, reversal, reattempt across different training stages.
using those clever automated methods to generate realistic error scenarios for training.
Right, both offline with synthesized data and online by learning directly from real failures in dynamic environments. And the experimental results really seem to show this comprehensive approach is highly effective.
Yeah, preventing that degradation of reflection skills seen in standard training, and significantly improving the agent's overall ability to handle complex tasks by making them much more resilient to errors.
It feels like a really foundational step towards creating AI agents that can navigate the messy, imperfect reality of our digital world with much greater robustness and, well, intelligence than we've seen before.
I agree. It's very promising work.
So here's a final provocative thought for you, our listener, to maybe mull over. We spend so much of our time on our devices, right?
Yeah.
Interacting with these complex apps and websites. And we inevitably make mistakes ourselves, a misclick here, a wrong turn in a menu there, maybe forgetting a crucial step. We recover because we can reflect. We can think, okay, that was wrong. Why did it go wrong? What should I do now? So as AI agents become more and more integrated into helping us with these digital tasks, how crucial is it really that they also possess this fundamental, almost human-like ability to understand when things go wrong and figure out how to fix them? What does this capacity for self-correction truly mean for how much we can ultimately trust automation with the increasingly complex digital workflows that shape so much of our modern lives?
It's a deep question. Maybe think about that next time you or maybe an automated process you're using gets stuck or frustrated on a website or in an app. This research is bringing us closer to a future where the software itself might be smart enough to lend a hand in navigating those digital frustrations, recognizing the error, and actually helping you or itself get back on track.